types of views. So one of the first multi-view learning algorithms is called co-training, and this one was proposed by Bloom and Mitchell. And this is some type of semi-supervised learning algorithm. So it's always better to work as a team than working individually. So the main idea is that you have two different classifiers. So you train one of the classifiers using one of the views, for example, the text inside the website, and you train the other classifier using the information from the links pointing to that website. So then you can start making predictions on your unlabeled training set with one of the classifiers, and you can use these predictions to enlarge the training set of the other classifier, and vice versa. So you perform this iteratively, and over time, both classifiers will help each other, and hopefully the accuracy will increase. So that's the basic idea. This is the sequence of steps. This is the pseudocode for the algorithm. So we have our set of labeled instances and our set of unlabeled examples. And it has been shown that empirically that sometimes it's helpful to create a pool called U prime by choosing some random number of examples from the entire unlabeled training set. So you can define some k iterations, and in each iteration, as I mentioned before, you train one of the classifiers and use the predictions to enlarge the training set of the other classifier. And can you spot any problems with this approach? Well, one of the issues is that what happens if one of the algorithms classifies a data point as positive, but the other one classifies it as negative. So we can end up having some conflicts here. So how to deal with these conflicts? One way is to maybe just take the prediction with highest probability, or you can also multiply the probabilities among the two classifiers and take the maximum probability. And also, in order to avoid this type of conflicts, some implementations use independent labeled training sets for each of the classifiers. So there are some assumptions if you want to use this type of methods. So a feature split into two different views exists. And the next one is important. Each feature split is sufficient to train a good classifier. So you need to be able to train a good classifier from the beginning for both of the views, because if one of the classifiers is failing or is not getting very good accuracies, then it will impact the other classifier and the error will propagate, and it will be a mess. Instead of getting a good classifier, we will end up having something useless. And we also have another assumption that the views are conditionally independent given the class, but this assumption can be relaxed, so it's not a very strict assumption. So how can we combine the results once the iterations are done? Well, as I mentioned before, we can also multiply the output probabilities for both of the classifiers and for each of the predictions, and just select the one with the maximum probability. Or you can also choose the class with the maximum probability among the two models. Or you can, in the final iteration, just train a single model with the union of both data sets, in the case if you decided to implement two different training sets for both of the classifiers. So any questions? And later on, in order to deal with this type of conflicts, Xu and Li came up with this idea of having these three training algorithms. So instead of having just two learners, we will have three learners. And the idea is rather simple. If two of the learners agree, then that data point is used to teach the third learner. So to summarize these topics, I included here kind of a poem, which is called From Co-training to Retraining, and it goes like this. One sees light, and the other one sees dark, but they always work together to enlarge the training set. Sometimes they disagree, so they keep independent labeled sets, but at the end they always become friends. Well, sometimes they make mistakes and they will propagate, causing the overall performance to degrade. Fortunately, one day they make a new learner, and whenever they agree, the data point is shared with it. Now the three train together, predict together, and will live forever. And here is a list of some supporting materials that you can use to learn more about these multi-view learning and co-training topics. The first one is the original paper from Bloom and Mitchell about co-training. And this is the original paper about tree training. And this is an entire book that deals with the problem of semi-supervised learning approaches. And the next topic is called stacked generalization, which is a method that involves building very powerful classifiers and somehow combining the predictions of those classifiers to create an even more powerful classifier. So stacked generalization was proposed by Wolpert in 1992, and in the original paper he used neural networks for regression problems, but also for classification problems. And the basic idea is to combine powerful base level classifiers or learners by stacking their outputs. And many of the Kaggle's winning solutions use some type of stacking. So if you want to win competitions, then you should use some type of generalized stacking methods. And well, this is just the Superman's logo, and I just use it because that's my favorite superhero. So for instance, support vector machines are very powerful at classification tasks. But now you have LSTMs and recurrent neural networks, which are also very powerful and state-of-the-art. And we have also random forests, which are also one of my favorite classifiers. But if you put all of those together, then you should get a super learner that hopefully will have a higher accuracy, or that will be better than any of the other individual models. So that's the basic idea. And the steps are very simple. You just train a set of first-level learners, and then you use the outputs of the first-level learners to train another learner, which is usually called the meta-learner. So this is the first view. So graphically, this is how the procedure looks like. You have n data points in your training dataset, and you have L different learners. So you make predictions with your L different learners and store those predictions in some vectors. And then you just column bind those vectors to create this resulting matrix, M, which has n rows and L columns. And then you just append your original ground truth labels to that dataset, and you use this to train another learner, which is called the meta learner. And these are the details of the sequence of steps. So first you find a set of L first level learners and a meta learner. This can be any type of method. You can use neural networks, CNNs, random forests, whatever, or you can use combinations of those. That's the good thing about this type of method, because this method was developed like in 1992, but you can still use it with state-of-the-art algorithms. And then you can use these first-level learners to train. You can use a data set D to train these first-level learners, and then you can predict labels for that data set using those first-level learners. And you just stack those predictions to create our matrix N. And by using this matrix, then you can train the meta learner. So steps 2 and 3 of this, yes?
Do you again only use the points if all the previous learners agree, or do you still use them if they disagree? The points from the first level learners, if they say like different things, do you still use all of them?
Yeah. Of course, if you have, for example, 2 base level learners, one of those may classify a point as positive and the other one as negative. Even if they disagree, you still need to include them in your final matrix. And yeah.
Why do you use only the label output and not the latent output from the previous current classifiers?
Yeah, sorry, could you repeat?
Why do you use only the labels you get out of the classifiers and not the latent output, like cutting off the last layer?
You mean
Because
like
you
like
lose
the
information, right?
Yeah, so you mean like the confidence score of each of the predictions?
Yeah.
Yeah, we'll take a look at that in the following slides. Hopefully that will answer. So there is a problem in steps 2 and 3, which can lead to overfitting. Can you spot what's the problem in these two steps? Well, the problem here is that we are training the first level learners using our training data D. And again, we are making predictions on the same training data D. So we are using the same data set for training and testing, and that's not a very good way of doing things. So how can we avoid this? Then we can use an inner k-fold cross validation within these steps to avoid this type of overfitting. And after our newly created data set has been generated, then we can retrain all of our first level learners with all data from the, for example, if we want to deploy our system in real time or in a production system. So as you mentioned, some information will be lost because we are just adding the final predictions. But you can always add some confidence information about the predictions. So in this case, we can add an additional matrix of size n by k, where n is the number of our observations and k is the number of classes. So most of the classifiers are capable of generating some type of confidence score or probabilities. So you can include those in this matrix to add more information to your data set. So you just concatenate this newly created matrix with your previous predictions and form your matrix M and proceed as usual. I don't know, yes?
So are you just matrix multiplication with multiplying M with Y in the meta learner? Is
In
it,
this case, we are concatenating these vectors.
Yeah.
But concatenation is the operation, and in this case, this symbol here means also concatenation.
Yeah, but the D mark, is that just a multiplication of M times Y?
You mean this D?
Yeah. Yeah.
Oh no, sorry. This is also concatenation.
Okay.
Yeah, to indicate that you put together this matrix M. These are your predictor variables, and these are your labels, for example, your positives or negatives. So I don't know if this answered your question about.
I thought it would be better to include the latent information you get out of the previous trained classifiers. So it's a difference if you have the confidences you get out, like this, probabilities, and information you get out like layer before the last, right? So you could just stack the output in the middle of the classifiers. You would have more information.
Yeah, by layer you mean for neural networks?
Yeah, exactly.
Yeah. Yeah, it will be possible also to use information from the previous layers in the case for neural networks. And this method is general, so this is the basic idea, so you can apply it even for decision trees or name-based, even if they are not connectionist algorithms. And these are two useful resources if you want to learn more about stat generalization. This is a book called Ensemble Methods. And this is the original paper from Walter that explains the whole idea. And now I am going to talk about data representation. And this is related to multi-view learning and semi-supervised learning. So yeah, you can use also this too. in conjunction with multi-view learning techniques or co-training learning techniques. So every time you want to solve a problem, it's useful or it's crucial to select a good data representation. For example, as Charles mentioned yesterday, if you want to represent music, you can do it with a vector of values, but you can also use an image to represent the same type of information. So it's worth investing some time thinking about the possibilities of how you can represent your problem and how you can model it in order to get the most out of it and try to capture as much information as possible from your real world phenomena that you are trying to model. So each representation provides a different perspective or view of your problem, and as a consequence, each view will provide different types of information that your algorithms can use to find the desired patterns. So the predictive models will heavily depend on the type of representation that you choose. So now I'm going to talk about some data representations. This is the most common one, I think, feature vectors. So with feature vectors, you try to model some real object or some real behavior or situation and put everything into a single array of numbers. So for instance, if we want to classify plants or types of plants, then we can create a feature vector. And for example, the first value could represent the number of petals, and the second value could represent maybe the third value could represent the average distance between the centroid and each of the corners and so on. And this type of representation is very efficient, and most of the machine learning algorithms support this type of data representation. And for example, for signal processing, you can extract time or frequency domain features and convert them into feature vectors. And well, this is like a kind of a disadvantage because this requires a bit of feature engineering. So you need to know about the domain, and you need to think about what features will be relevant for your specific problem or use case. And one of the problems with this representation is that substantial information can be lost. For example, if what you are trying to model has temporal dependencies, these temporal dependencies will be lost because this type of representation is static. Another type of representation that you can use is just raw time series data, for example, for weather data or temperature, solar irradiation, or music, and so on. And the advantage of this type of representation is that they preserve temporal patterns as opposed to a feature vector representation, because you are just using your entire data. You are not doing any feature extraction or any compression. The downside is that not many models support handling this type of data, like time series data. And sometimes it can be computationally expensive. And there are some methods that are suitable for time series classification. For example, just the Euclidean distance. So this is a very simple method, but surprisingly, it provides sometimes state-of-the-art results for classification tasks. So you just need to compare your query time series data against your database, and you just assign the label of the closest time series. There's another method called dynamic time warping, which is similar to Euclidean distance. So sometimes you may have a time series like this one. They look similar, but for example, the second time series is a bit shifted to the right in this portion. And here it's like it's, well, in this case they look similar, but here this point is a bit shifted to the right. So with dynamic time warping, what you do is to try to first align these two time series over time, and then you compute the Euclidean distance once these time series are aligned on time. So sometimes this can produce better results than using a pure Euclidean distance approach. And another really cool method is called shadelets, because they provide interpretable results. It's not like a black box, so you can actually plot the resulting model and see what's happening. So what's a shadelet? A shadelet is just a subsequence that maximally discriminates between two different classes. So in this case, an algorithm will try to find the best shapelet that will help you to separate or differentiate between two different classes. For example, here if we wanted to classify shields, different types of shields, then we can just run the algorithm and it will find the most distinctive shapelet, which is a subsequence of the entire image. And you can just overlay this shapelet on the original image and see what are the differences among these two classes. For example, here it seems like the Spanish shield is more curved than this one. And so if you want to have interpretable results, this is a good option. And finally, LSTMs, which provide state-of-the-art results and are also capable of working with raw time series data. Another data representations are images, so if you are planning to classify images, then you are already done. So you can use, for example, CNNs. They are very efficient for classifying images, and they also support multiple dimensions in the case of RGB images or color images. But the nice thing is that you can play around with your data and you can make transformations. If you have a time series data, you can convert it to an image and use a CNN to perform classification. So if you have an audio file, you can compute the spectrogram, for example, from a violin, and then use these images to train a CNN. Or if you have some time series data that looks like this, you can compute a recurrence plot, which is also kind of an image, and train CNNs. So a recurrence plot is just a visualization tool to plot and to understand a dynamical complex system. And these things require some expertise to interpret, but hopefully we can use CNNs and they will do the job for us. So as you can see, you can have a time series signal, and by converting it into an image, then you are extracting more information rather than maybe just using the raw time series data. Another type of representation is called back of words, and this is very common for natural language processing tasks. So if you have a set of documents and you want to classify the topic, you want to know if this document is about medicine or computer science, laws, and so on, then you can just extract all the words and represent them as a back of words. And how do you do that? Well, you just plot the frequencies of each of your words. For instance, if you have an article about medicine, you may have the cancer word appearing a lot of times. Well, I don't know why I like this cancer thing. I should choose another, a more positive example instead. But anyway, and maybe if you choose a computer science document, then here most of the words will talk about computers, or I don't know. So once you have this distribution of words, you can use it as a feature vector to train any classifier. And the nice thing about these back of words is that they are also using computer vision, so they also work with images, not just with text. And you can also convert time series data into a back of words representation by using, for example, vector quantization. And the disadvantage of this type of representation is that temporal information is lost. So once we have this representation, we don't know which words came before other words. But in some cases, this does not matter. But of course, this will also depend on our use case and application. And another representation that we can use to model our problem is by using graphs. This is a very general data structure. And it's really nice because you can model a lot of things using graphs. So you have nodes and you have edges. So you can capture relationships between entities, and these edges can be weighted. Also, each node can have an associated value. So for the document example, you can represent words as nodes, and edges can represent connections between adjacent words. And once you have this type of representation, you can use the adjacency matrix. And adjacency matrix is the matrix representation of a graph. So it captures the connection between nodes and the weights of the edges. And you can be creative here and use this adjacency matrix as an image and train a CNN. Or if you have this one, you can also compute some statistics, for example, closeness centrality, which will tell you on average how close a node is to every other node. And you can also compute, for example, the betweenness centrality, which means this is a measure of how popular a node is, or if you have a path between any given node, then a node will have high betweenness centrality if most of the paths go through that node. And you can also compute, for example, the inbound, outbound number of edges, and so on, and build feature vectors on. There's a lot of potential for creativity here, so you can combine, transform your data and create new representations to use different models. So why am I talking about these data representations? Well, because it's possible to generate or combine different representations. And for instance, if you want to classify audio files, you can extract statistical features from them and use a support vector machine. But you can also compute a spectrogram and use a CNN, or you can use the raw audio data and train an LSTM. And finally, you can use stacking to get the final prediction. And indeed, one of the proposed projects is about using something like this, generating different representations and using generalized stacking to produce the final predictions. And I also wanted to include this topic, which is called multi-user evaluation. So sometimes we build systems that are going to be used by humans. So users are unique. They possess different characteristics and behaviors. And we have different attributes like age, gender, height, and so on. So these type of attributes may impact your performance when deploying into real life applications. Some multi-user scenarios are speech recognition, hand gesture recognition, activity recognition, facial expression recognition, and so on. So for instance, we did some weeks ago some experiments for speech recognition. So we wanted to train a model to detect mood based on speech. And in this data set has males and females. So we trained a model using just males and tested it with a female user. And the accuracy was very bad. Why? Because speech between genders is very difficult and varies a lot. So this is just an example of how user attributes can affect your models. In the case of activity recognition, if you want to recognize if a person is running or walking or so on, then maybe age will be important, because maybe young people tend to walk faster than babies, or I don't know. So these are considerations that need to be taken into account when building systems that are going to be used by humans. And there are some evaluation strategies to test the performance of this type of models. One is called mixed models. The other one is called general models, and the other one is personal models. Mixed models do not make a distinction between users. So you just aggregate all your data, and regardless of users, you perform tenfold cross-validation, for example, as usual, and report your final results. The disadvantage of this is that some data points of the same user can end up in the training set, but also in the testing set. So you will get overestimated performance results, and when you deploy your system in real life, then you will realize that the performance is not as good as you thought it was going to be. So using a mixed model approach to validate data set with multi-users is not always a good idea. And another technique you can use is to train personal models, which just means train a model for each specific user independently of the others. And in general, the performance will be very good because you are targeting each model specifically to each particular user. So you are capturing all the patterns for that user. The disadvantage of this is that they require more data for each of the users. And as I mentioned before, collecting data is expensive and time consuming. and they are also prone to overfitting. Another approach is to build general models. So these are not trained with data from the target user. So the advantage of this type of models is that they can be used right away to make predictions. They don't need any fine tuning or any additional training data for new users. But the disadvantage is that the performance can be very low for some users or even for all of them. So how to train this type of general models? Then you have a set of users in your database, and this approach is called leave one user out validation. So it just means that you take one of the users and use his or her data as the testing set, and you train a model with the remaining users, and you repeat the process for each user. And here are some supporting materials about multi-user evaluation. And finally, the final topic, which is called baseline classifiers. So machine learning is not the answer to any problem. Sometimes we are biased towards using machine learning for everything. So we want to solve everything with machine learning. And nowadays, a lot of companies are hiring a lot of people to do machine learning, but they don't even have a problem to solve. So surprisingly, you can solve many of those problems using simple heuristics. And the baseline classifiers will allow you to assess whether or not machine learning has a benefit. So as Bruno mentioned yesterday, it's always a good idea to compare your methods to some baseline algorithms or with other state-of-the-art methods. So some of the baseline classifiers that you can use are just predict the most frequent class. If you have cats and dogs in your dataset and most of your data points belong to the dog class, then just always predict a dog. So you can also predict according to prior class distributions. Or you can also predict uniformly at random. Or if you have a time series data, you can predict the average value for a given day or a given hour. For example, if you are trying to predict temperature, just predict the average temperature for the same day and for the same hour of the day. And that's a good baseline classifier. Or if you are also trying to predict time series data, then you may build a classifier that just predicts the next observation, having the same value as the previous one. So this may seem like dumb solutions, but it's common that sometimes it's really difficult to beat these baseline classifiers using state-of-the-art machine learning models. So yeah, it's always a good idea to try these baseline classifiers and see if machine learning is really providing some benefits. And scikit-learn, which is a Python library, already contains a class called dummy classifier. And this implementation has, for example, the uniform method, which generates predictions uniformly at random, and also this prior, which makes predictions according to the prior probabilities and so on. So you can use these type of tools. Yeah, so any questions from any of those covered topics? Yes?
So in the stacked generalization,
Yeah.
the meta learner, would that be just a learner that you can choose
Yeah, you can choose.
like you want?
Yeah.
Okay.
So for instance, here you can have a random forest or vector machine, neural networks, and you can choose another one for a meta learner like neural network or random forest, whatever. Yeah.
Would there be any significant difference? Or say that you have like model 1, 2, and 3. Would there be any significant difference of choosing 1, 2, or 3 as the meta learner? Or would it be like
Likely there are going to be differences. So that's an interesting problem. So maybe you can use some optimization technique to try to find the optimal classifiers to use at each of the levels, and to automatically select which are the best base level learners, but also what is the best meta learner. So that would be a problem in itself, worth exploring. Yeah.
I don't know if you know me. I work here in the Robin Group as a postdoc, and the reason I ask these questions is that I don't really have that much contact with the teaching parts of this university. I'm here every day working on research. I supervise individual master's students, but I don't know what you guys do in your courses exactly, or how many people have taken the previous courses. So part of why I'm asking that is because this presentation comes from work that I was presenting to other researchers. So it was kind of pitched at the level of people who maybe don't know everything about neural networks but know a little bit, or they might have some knowledge which is out of date and they want to catch up on RNNs. And also professional researchers are confident that if they don't know something, they go and read a book or figure it out. So this now coming to you, the level is information that's fairly high level. If you've got more questions about it, that's fine. Not all of the answers are here. I'm giving an overview of something which is quite a deep topic, and if you want to know more, there's a lot of reading for you to do. You could be looking at reading one of the papers for your paper presentation that's to do with RNNs, or you could just do some learning as part of this course on your own time. So if you do have questions about it, write them down or put your hand up during the session. I'm happy to go into some more depth, but also not all the information is here, so do some more work if you feel you want to find out more detailed information. So, artificial neurons. Now, many of you have taken the bio-inspired computing course, so you might have seen a slide like this. Artificial neural networks are made of artificial neurons. These are very simple mathematical units that in some way are supposed to be similar to neurons in your brain, okay? But in many ways they're completely different, right? It's a very, very rough approximation. I guess in some sense they sort of look similar, and maybe neurons in your brain have inputs and outputs, but really that's where the similarities start to end. There are some bio-inspired systems which have very detailed representations of biological neurons, but none of the deep learning neural networks are those. These are using very simple so-called artificial neurons. What does an artificial neuron do? Well, you've got multiple inputs on the left-hand side of this artificial neuron I've got here. X1, X2, and X3 are different numbers entering into this artificial neuron. Each of those numbers is weighted. You've got weights in your artificial neurons, right? That's controlling how much influence each of those inputs has. Then the weighted inputs are all summed together. That's the sigma sign. Then squashed with a function, nonlinear function, such as the sigmoid function or the hyperbolic tan function. And then you get some output, y, the squashed output of that. So that's artificial neurons. This is not news to anybody who's taken biologically inspired computing. Now, when you've got a neural network, a regular old feed-forward neural network, you've got some input here. The blue dot is the input on the left. And that might go to multiple artificial neurons, right? And then you might have multiple layers of artificial neurons with many connections going between them. And these ones are all fully connected. So each layer of neurons is connected to each neuron is connected to every one in the subsequent layer. Feed-forward networks. So with this, when you give it some input, suppose it's 1, and you get an output, that might be 10. Cool. Then you give it another input, 3, the output's 30. That's great too. But there's nothing about this neural network that means that cares about the fact that you gave it 1 first and then 3 now. It's every time you give it some input, there's some output, and there's no information stored inside it. But what we're talking about today are recurrent neural networks. These are neural networks that do care what your previous input was. So you give it a 1, you get 10. You give it a 3, it gives you 30. But if you had actually given it a 2 in the first place, maybe when you give it a 3, it gives you 50 instead. So there's something about the fact your previous inputs which is influencing the current ones. Now, I'm introducing on this slide a little bit of notation which I'll use throughout this talk, which is this little link with a box on it. Do you see that? And in this talk, the little link with a box on it is just the same as a regular connection in a feed-forward neural network, except it's time delayed by 1 step. So the outputs from all of those neurons goes up to the box, and it sort of waits there until you give it some more input, and then it proceeds from the box to the input of each of those artificial neurons. So that's recurrent networks. All they do is store a little bit of information. Okay? Why is that useful? Well, there's many, as I told you on Monday, or discussed a little bit, there's many tasks for which having some context about previous inputs is useful for making good decisions. One of those tasks is text generation, right? If you're picking what word to put next in a sentence, suppose I give you the word little. What's the next word in the sentence? Anyone guess? What comes after little? No one's has me a guess. Why is the reason no one's has me a guess? Not even prepared to guess. Because it's such a stupid question. Almost any word can come after little, right? What if I said twinkle, twinkle, little star? Yeah, now it's obvious, right? So if you have some context, that prediction problem, predicting what word's going to come next, becomes much easier. So these recurrent neural networks let us keep some context around inside our neural network so that the prediction becomes easier based on the previous information we've been given. Some of the problems we're going to talk about today is using these recurrent neural networks to predict text letter by letter, such as in that character prediction task. Another thing I like to do is to predict music note by note. You can also use recurrent neural networks for that. And then there's many other kinds of tasks which I might go over a little bit, but things that interest me in particular are artistic tasks such as predicting harmony from a given melody or predicting reactions in an ensemble of musicians to a certain main line, sequence learning. Okay, so I showed you that recurrent neural network before, and I'm just going to do a little bit more notation now. So before I had all those fully connected units and there were many artificial neurons, but now I'm going to simplify that so that each layer of those artificial neurons is just going to be one of these boxes, right? Each of these boxes is an abstraction for many recurrent neurons, and then I've got one recurrent link. So rather than a single number in that arrow, it's now a vector of numbers representing the state of the stored state of each of those layers of neurons. And I'm going to simplify a little bit further and turn everything vertically, and this is the way that the rest of the lecture is going to be going, just so you don't get confused. So now we're starting to provide some more information about how this very simple example of a recurrent neural network works. Okay, so we've got our input, which I'm calling x, and I've got our output, which I'm calling y hat, and then I've got a number in the middle, which is h. And h is going to be the state of that neural network. So that's the bit which is stored in between evaluations or computations. And then I've got three other letters here, u, v, and w. What does u, v, and w represent? What do you reckon? Has anyone seen this kind of notation before? So what was that? Very quiet. Someone give me the answer. Oh, yeah.
Input vector for u and output vector for y, or w.
Wow.
V is some sort of weight for the...
Yeah. They're actually, the idea is that all of these would be weights. So all of these are matrices of weights that would be applied to the vectors. The vectors have a lowercase letter and the matrices have an uppercase letter in this notation. So x is a vector, h is a vector, y hat's a vector, and u, w, and v are weights that are applied to each of those vectors. I'll show you how that would work in a minute. So let's start to figure out what these letters mean. And we're really particularly interested in figuring out what this h is, this state which is stored in between computations. So I've said that recurrent networks are all about storing this state, this h, a vector. And one way of putting this is that it's a lossy summary of previous sequences that you've seen, some representation of all of the previous information that the network has had. Now, what influences h? Let's have a look at a mathematical representation of this. What's coming into h from in our diagram? Can someone tell me what's influencing it? You can either use the diagram or the maths to figure this out. Come on, someone give me a guess. What's influencing H? Yeah.
The weight input and former weight memory
Yeah, exactly.
and the bias node.
Yeah, that's right. So